practice problem number 1. Classify the following as physical or chemical changes.
I want this one.
Of course you do. Smashing a vase. Because you change it. Smashing pumpkins. What is, right? Is that a physical or chemical change?
Physical.
Okay, so we haven't reacted to anything, right? All we've done is change its appearance. It used to be a vase. Now it's a bunch of vase pieces, but they're still little atoms of vase, right? Of vaseness. Okay. Making a cake.
Chemical.
It's a chemical change. You're doing more than just changing the way it looks when you make a cake. The heat of baking actually causes chemical reactions to take place in the ingredients. Okay, so what you end up with at the end is different chemically than what you started with the ingredients mixed together. It's not simply looking different, it is different. Okay. And you ever notice when you bite into a piece of cake and it didn't get thoroughly mixed all the way through, and you've got pieces of like baking soda or baking powder or flour in different places, and you get chunks, and then you got the powder in your mouth. That's the stuff that didn't have time to, didn't get an opportunity to react. Okay, so you're eating the elemental, the reactant form, not the product form. But making a cake is actually chemical, and the heat of baking, that might have been part of the clue. The heat of baking is the energy required for the reaction to occur. Okay. I just wrote this as sublimation because it said in here dry ice becoming a gas. Is that a physical or a chemical change? It's a change of phase, right? That's all. It's a physical change. Right? It doesn't, it's still carbon dioxide, whether it's in dry ice form or we don't talk about liquid carbon dioxide because it tends to sublimate straight to a gas. So whether it's in the gas form in this question, whether it's in solid form or gaseous form, its formula is still CO2. It's just in a different phase. And phase changes are physical changes. Burning charcoal. Chemical. If it's burning, okay, something is happening. The heat, and the thing about fires is they're self-perpetuating. It takes heat to start a fire, but once you have a fire, the fire provides the heat for the future fire. Okay, that's why wildfires take off. It just takes one spark. That's the energy for the first fire, but then the fire creates the energy for future fire. And it keeps going and going and going and going until it runs out of fuel, runs out of what else? So whether the fuel to burn, the carbon-based fuel to burn, the oxygen as part of the combustion, or heat. And that's why they're talking right now in California, the Santa Ana winds. Has anybody else here lived in California before? Okay, the Santa Ana winds are hot winds that come off the desert, as opposed to ocean breezes, which are cool breezes that come off the water. Coming off the desert, they're hot and they're dry. Okay, and the problem is they're fanning these wildfires in California. So the air that's blowing in is actually, I don't say so much as giving energy to the fires as much as it's not quelling or quenching the fires. And it's forcing the fires, pushing the fires onto new fuel. And since the fire already has enough heat and has enough fuel and has enough oxygen from these fresh winds blowing in as well, it makes them flare up and get really, really strong. Now, if the winds were to change and suddenly come off of the ocean, I'm not saying that the ocean winds would put the fire out, but what I am saying is they wouldn't encourage the fires as much. They may blow the fire into different areas, but the cooler air coming in has less inherent energy in it than the hot air does, you see? Plus the cool air coming in has water vapor in it, which is going to have an effect upon the intensity of the fire as well. But it's a self-perpetuating chemical reaction. That's what burning is, a self-perpetuating chemical reaction. So this is a chemical change. And lastly, making Kool-Aid. Junior scientists, right? Is making Kool-Aid a chemical or a physical change? It's physical. You're just dissolving the components into water, the sugars and the dyes, that's all it is, right? And you're not creating you're not exploding anything. All you're doing is putting water molecules between all the different components that make up a packet of Kool-Aid. So, all right. Number 2. Lead has a density of 11.4 grams per milliliter. If you make a statue out of 3.45 liters of lead, what is the statue's mass? Okay, so we have to start with our density equation. Now, at least one person here likes to use D for density. Don't do that. The standard abbreviation is rho, the kind of a cursive looking P. okay? That's the symbol for density. Now, if you use D on your work and you use it correctly, doesn't mean necessarily took stuff off, but you're going to create confusion later on. So try to stick to the standard abbreviations. In chemistry and in physics and basically in science, rho, lowercase here, is the standard symbol for density. You put that on a piece of paper for anybody that's in the sciences and they'll know what you're talking about. If you put D, they're going to assume it's distance. Okay. So we're asked to solve for what is the statue's mass. So we have our density equation. We've been given the density and the volume, and we're told to solve for mass. So what does it look like rearranged solving this for mass? Yes, sir?
M equals density times velocity.
Volume. Density and volume. So the mass is a density times the volume. Think about it. It's grams per milliliter times milliliters. So it's going to be grams, right? Because the milliliters are going to cancel themselves out in terms of the units. So the mass is equal to the density times the volume. In this problem here, we're given that the mass is 11.4 grams. That's a typo already. It's 11.4 grams per milliliter. It's not grams, but grams per milliliter. That's the density, right? That's indicating how much stuff is packed into every milliliter of lead. There's 11.4 grams of matter for every milliliter of lead. So rho, or mass equals rho. Mass is 11.4. The volume is 3.45 liters. So again, we plug this one. This should be rho, and this should be grams per milliliter, right? Is that my typo? Do you agree? We're on practice problem. For those of you, practice problem number 2. So 11.4 grams per milliliter and 3.45 liters. So what is the mass? Well, the mass is, or excuse me, I rewrote the volume here in terms of milliliters, right? Some of you didn't do that, but our density is in grams per milliliter. We need to make sure we have the same volume units as is used in the density. The standards for density are grams per milliliter. So you should assume that you're going to translate the volume into milliliters. So the mass is equal to the density, 11.4 grams per milliliter. See, my units are all messed up. Sorry, I copied another problem and tried to change it real quick. 11.4 grams per milliliter times 3.45 times 10 to the third milliliters, and that's going to give us a unit of grams. Okay, and that turns out to be 3.93 times 10 to the fourth grams. But it's really just an application of the rho equals m, mass divided by the volume, or the equation for density, and being able to rearrange that. Hopefully there are not nearly as many typos on 603. To be honest with you, I intended to do this whole thing on the whiteboard, and about 20 minutes before class decided to put the slides together. So what you're going to see on slides today, I did in about 20 minutes, and didn't have an opportunity to go through and proof them like I normally do. So I apologize for that, but I think it's maybe a little bit advantage to do at least the first 7 like this. Hopefully the typos clear themselves out. In 603, it says gold has a density of 19.3 grams per cubic centimeter. If a gold nugget has a mass of 45.6 kilograms, what is its volume? So again, what is the primary starting point we have for this problem? Where are we going to start to first investigate to try to solve? Ma'am?
You have to rearrange the density formula.
Right, we're going to start with the density formula again. This time, we're asked to solve for the volume, the V. Okay, so we have to rearrange this formula to solve for V, volume. And that comes out to be that volume is equal to the mass divided by the density. Again, I can't really go and reteach the algebra on how to do this, but hopefully you can do that on your own. You can rearrange the formula to solve for the unknown. In this case, the unknown is the volume. If you want to think of it this way, what we did was basically slide the volume above and took the rho and slid it below, if you know the shortcuts. But in any case, rearrange the density formula to solve for volume. Mass we were given here Did it again. 19.3. Did I do it again? No, I didn't. Good, I got it right. Surprisingly, I got it right. Doesn't happen all the time, as you know. The gold nugget has a mass of 45.6 kilograms. Standard unit is grams for density. If we look over at our density here, we've been given 19.3 grams per cubic centimeter. So we've got to get it in the language of grams. And again, if you need to write out the conversion factor of kilograms times 1,000 grams per kilogram to work it out, but at this point you should be able to convert from grams or from kilograms to grams using scientific notation pretty quickly. So 45.6 kilograms is 4.65 times 10 to the fourth grams. And then we had a density of 19.3 grams per milliliter. So the volume is the mass divided by the density, or 2.36 times 10 to the third milliliters. Now, for some of these questions, when you get your homework sheets back, you're going to see that the answers that you have are close. You might look at it and go, oh, he took off that many points for just this little mistake? That little mistake, unfortunately, if you do the problem and you invert a couple of these problems, if you do them in the inverted manner, you get an answer that's similar but not the same, and it's close. So it's not that you're off by a 2 or 3. That appears to be off by 2 or 3, but it's really, look at the scientific notation, it's in relation to doing the problem inverted. Like in this case, if you did V over M, you know, you might get an answer, not in this particular one, but you might get an answer that looks similar. But it was set up and done wrong. So, guys are lacking a lot of energy today. Was it up too late last night or what? What's going on? Okay. Thank you for that positive input of why you're not like everybody else. Is there something going on?
I think it's just we all have a lot of school to do this week, so it's just a combination of stress and not enough sleep.
Okay. Me too. I've got to grade 350 pages of essays before tomorrow. How am I going to read and grade 350 pages? Because I've got students that want to graduate from seminary on Saturday and need their grades. Okay. You either just give them a grade without reading it, which would not be fair to them, right? It wouldn't be fair to the people who did the work, and it'd be unfair to the people who didn't do the work too. So I guess I just have a lot of work to do tonight. And I'm working on a 30-page paper too that is due before Tuesday. So I'm with you on that. Okay. Let's go ahead and ask the question, is this balanced? This equation. Well, before we can answer the question, of course, we're going to go through our process. And I'm doing a lot of talking right now because I'm going to give you guys the floor for the last 3, okay? Just so you know. We look at the equation and look at the elements that are involved. And this is a process. I know you haven't heard this as many times because you've been gone. And I'm not using your name because of the video. I don't have to go through and edit it out. But you haven't seen this a lot because of your time away. But in the other YouTube videos, you can see this. The process we're trying to instill on whether finding out if it's balanced or to balance it, because balancing an equation just means checking if it's balanced repeatedly, and when it's not balanced, tweaking it. So you're going to do this process over and over and over again. So let me just go ahead and say what we do. We see the reaction equation, and we immediately go through it, and first thing we're going to do is make a column of all the elements that are involved in the reaction. And so we look from left to right, and we come across calcium, we come across fluorine, we come across nitrogen, we come across hydrogen, we come across chlorine, and now we're on the other side, and we've got calcium, fluorine, nitrogen, hydrogen, chlorine, nothing else, nothing new. So what we have on the left and what we have on the right, they're all accounted for in this column of elements. Remember, you can't lose or gain any atoms of any element. You have to have the same number of every building block before and after the reaction. And that's what we're trying to prove. And that's what we're trying to get an equation that states that accurately. Okay? So this might be, for example, if this is not balanced, it might be just, hey, this and this happens. Matter of fact, I think one of the real easy ones, number 7, an automobile, nitrogen and oxygen react. Okay. First of all, you just write down what the reaction looks like. Then you go through and balance it to make sure that's true. Because this might be describing the reaction, but it may not be true. But if it's balanced, now we have a true statement. So we've looked at every element that's involved in the reaction. And then we go through and we count up all the atoms, first of all on the reactant side, second on the product side. And if they all match, in other words, if we have the same count for every element before and after the reaction arrow, it's balanced. And if we don't, it's unbalanced. So this is a yes or no question. Okay. On a couple of your homeworks I wrote down, so the answer is no, because you went through and gave me the balanced reaction and it wasn't what you started with, so therefore it must have started unbalanced. You did a lot of work to answer a yes or no question. Question was, is it balanced? You only need to do one time and you have an answer, right? So, counting up the calcium on the left, we have one set of 1. Fluorine, we have one set of 2. Nitrogen, it only appears here and it's 2 sets of 1. Hydrogen, it only appears here and it's 2 sets of 4, which is 8. And chlorine, we have got 2 sets of 1. Or excuse me. Yep, I did it wrong. So chlorine should be 2. I could write on the whiteboard, but it won't come across on the video. So I have 2 chlorines. I have 2 sets of 1, which is 2. Luckily, I made the same error on the product side, so we're good to go, because if I look at this now, calcium on this side, I have 1 set of 1. Fluorine, I have 1 set of 1. Nitrogen, I have, 1 set of 1. Guess what? I'm done. Because as soon as I find one that's not balanced, the whole thing is unbalanced. So the answer now I know is no. But I keep going and look at hydrogen, see that I've got 1 set of 4, and chlorine, I miscount, see, chlorine actually did that one right on the other side, 1 set of 2 on the calcium chloride. So this actually should be showing a balance, but it's not, because I've got 2 sets of 1 here, it should be 2. The only thing that's, these two are off right here, nitrogen and hydrogen. But as soon as I found the first one that was unbalanced, the whole thing is unbalanced, and I could stop, write no on my paper, and move on. I don't have to go through and balance it. You weren't asked to do that. So on the test, if you get this really complicated equation that says, is it balanced, yes or no, don't spend half an hour balancing it. You weren't asked to balance it. You just have to check it one time, yes or no, move on. If you spend a lot of time on it, you're probably going to write no in the end when you go, that's not what they're asking. I've got 7 tries. Why isn't it working? Because it's so complicated that if you get on a rabbit trail that you're not supposed to be on, it's going to eat up all your time. This one says balance the equation. So now you're in it till it's over. Now you've got to do 2, 3, 4, however many iterations it takes. So the same process. We're going to look at it and say, okay, hydrochloric acid and zinc are going to react to form zinc chloride and hydrogen gas. I think this one had phase symbols on it. You know what? I think for brevity, I just dropped them. I didn't put them on there. First, I had 20 minutes to type all these up. Second, if it's true, a true reaction, the phases for us, for our purposes right now, don't really matter. These are the building blocks we're talking about before and after the reaction. So looking from left to right, the elements are hydrogen, chlorine, and zinc. Okay? Looking on the right, there's zinc, chlorine, and hydrogen. They're all accounted for. What are the counts? On the left, hydrogen is 1 set of 1, chlorine is 1 set of 1, zinc is 1 set of 1. And on the right, hydrogen is 1 set of 2, chlorine is 1 set of 2, and zinc is 1 set of 1. Okay, so it's not balanced. It's not balanced in the language here is, it's not balanced with respect to hydrogen and chlorine. Okay, it's not balanced with respect to hydrogen. It's not balanced with respect to chlorine. It is balanced with respect to zinc. So, again, our process is then to look at this and say, which of my reactants are not used up? Don't have any that are in that situation, right? All my reactants are used up. As a matter of fact, my next question is, which of my products claim more than I had? And start balancing them out. Well, that's what they're unbalanced with respect to, hydrogen and chlorine. If I look back over to my reactants, it's sweet because hydrogen and chlorine are both together. So when I change the coefficient on one, it affects both of them, right? And so if I say that I've used 2, but I've only used 1, in order to have 2 to use, I need to add a coefficient of 2. With that coefficient of 2, since I've changed the coefficient on one of my reactants, for right now, I'm going to reassess all my reactants. I don't do that on one of the later slides. But for right now, for process-wise, you just say, OK, I changed the coefficient on a reactant. I'm going to recount all my reactants. Do you have to? No. Is it a good process for where you're at right now in your understanding? Absolutely. It's worth the time. So I've changed the coefficient here, so let me reassess all my reactants. Hydrogen, I have 2 sets of 1. Chlorine, I have 2 sets of 1. Zinc, I have 1 set of 1. Is it balanced? It's balanced now. So this is the balanced reaction equation. What does this balanced reaction equation tell me right here? I know it doesn't have phase symbols on it, so we don't have to get into that. But what does this reaction equation tell me right here? OK. We'll repeat this then. What this balanced reaction equation tells me is that for every 2 molecules of hydrochloric acid that I react with 1 atom of zinc, it will produce 1 zinc chloride molecule and 1 molecule of homonuclear diatomic hydrogen. Okay? It tells me how many of each of the building blocks I have before and after the equation. Because I can't destroy them, I can't make anything, I just rearrange them, right? But it tells me what my relationship of my reactants has to be and what the relationships of my products will be when I'm done. What this is telling me, for every 2 that I react with 1, it's going to produce 1 and 1. How many molecules altogether do I start with here? How many molecules are in the reaction side? There are 2 distinct molecules, but how many pieces do I have? How many molecules am I trying to react? The very smallest possible reaction would be 3 molecules. 2 molecules of hydrochloric acid, or HCl, and 1 atom of zinc. If I had those 3 building blocks, okay, I could smash them up, the reaction, okay? And when the dust settles, which was not a product of the reaction, it was just participatory environment, right? So it's not part of the reaction. When the dust settles, what's going to be behind the curtain? 1 molecule of zinc chloride and 1 molecule of hydrogen. And if I used 20 molecules, I would have to react it with 10 molecules to produce 10 molecules and 10 molecules. And if I react 2,000 molecules with 1,000 molecules, it'll give me 1,000 molecules and 1,000 molecules. And if I use 2 bazillion molecules with 1 bazillion molecules, it will react to produce 1 bazillion molecules and 1 bazillion molecules. And, next module, if I react 2 moles of hydrochloric acid and 1 mole of zinc, it'll produce 1 mole of zinc chloride and 1 mole of hydrogen gas. It's incredibly important information that you get from a balanced reaction equation because it tells you what is the proportional relationship for this reaction between the reactants and the products. How much do I need? And if I have it, how much will I get? And if you don't have a balanced reaction equation, you cannot, again, the balanced reaction equation is like the perfect recipe. And if you have to break it down again, go simple, just think of it as this. This is the recipe for cupcakes. And when I make cupcakes and I use the perfect recipe, I get perfect cupcakes coming out the other side. But in chemistry, if I add 1 extra egg that the recipe calls for, in real baking we get a cakey cupcake, right? But in chemistry, what we get is perfect cupcakes and an egg left over. So if you're running a business, which would you rather do? Have the perfect recipe and everything you put into it comes out as product? Or would you rather every time you make a dozen cupcakes have to throw an egg away? Because you waste an egg, right? That's the analogy. That's where to get to. When you're talking about 1 molecule, no big deal. We're talking about 1 egg, not really a big deal. When you do this a bazillion times over and over and over again, it adds up to real loss. You know, it's like $5 here, $5 here, but then eventually, do that 1,000,000 times, it turns into real money. That's the idea. So that's what we get from the perfect balanced reaction, or excuse me, from the balanced reaction equation. So you have to be able to do a balanced reaction equation from this point forward. You know, in the Christmas Carol, because if you don't understand this, then nothing after will seem mysterious. In chemistry, you can't balance an equation. You really can't move on. You have to be able to balance the reaction equations. Number 6. So I had to go small font because there's a bazillion different atoms involved in this thing, right? The only way I could get it on a slide was to make it really small. So I apologize for that. But we're same process. Don't let all these subs and all this stuff get you scared. Just start the process. What's the process? Identify the elements. They're nitrogen, hydrogen, chlorine, oxygen, aluminum, sulfur. And I just do it from left to right. Nitrogen, hydrogen, chlorine, oxygen, aluminum, sulfur, oxygen again. Okay. Aluminum, chlorine, oxygen, nitrogen, hydrogen, sulfur, oxygen again. Okay. Got them all. Now we count them up. On the left side, nitrogen is one set of 1. Hydrogen is one set of 4. Chlorine only appears here, one set of 1. Oxygen appears in 2 places. I have one set of 3, and I have 3 sets of 4. One set of 3 and 3 sets of 4 for a total of 15. Okay, do you see 15 oxygens on the reactant side? Let me put a little accountability onto you. Does anybody not see how we counted up 15 oxygens on the reactant side? So lacking your response, you understand that 15, how we got 15. Okay, I'll assume that. Aluminum, we've got one set of 2. And sulfur, we've got 3 sets of 1. Okay. Looking over to the products. Nitrogen, how many do I have? Okay, so I have 2 sets of 1. Hydrogen, it only appears in the last molecule. Right, I have 2 sets of 4. Chlorine, it only appears in the first molecule. It appears once within the polyatomic ion, and we have 3 of those, so it's 3 sets of 1, which is 3. Oxygen, and the product side, it appears in 2 different molecules, right? So in the aluminum chlorate, how many oxygens do I have? Just in the aluminum chlorate. 9. 3 sets of 3. I have 9. And then in the ammonium sulfate, I have 1 set of 4 for a total of 13. Aluminum, or aluminium. Aluminum, I have 1 set of 1, right? Because aluminum only occurs here. There's 1 per molecule, and I only have 1 molecule. Okay. And then sulfur, it only appears in the ammonium sulfate, and there's 1 of them. So that's the process to this point. Next question we ask ourselves is, what?
I always forget how to word.
Okay, look at where it's unbalanced. Well, first of all, is it balanced or unbalanced? It's unbalanced, right? So where do we have reactant that is going unused? In other words, where do we have somewhere that the number in the reactants is higher than the number in the products? There's nothing magical about it. We could work the other way too. I'm trying to give you something standard to do every time. These last 2? Because, well, this is unmatched. Yeah, they're pretty much everything it's unbalanced with respect to everything, but aluminum and sulfur are the only 2 where we have more reactant than product. So if I did the slides according to the way, and I'm really nervous now because I normally have a printout of all my slides and I know what's coming, but in this case I don't. What did I do? I'm sitting there at my desk rushing. What did I do? What mistakes did I make? Let's find out. So we need to we have 2 aluminum and 3 sulfurs that we need to use up, right? What did I do? Oh, I did them both at the same time. Do you see that? Because look at what happened. Aluminum, I need to use up 2. And sulfur, I need to use up 3. But aluminum only appears in this molecule here. And sulfur only appears in this molecule here on the product side. So I did a twofer. I said, because I can put a 2 in front of this, because that's the only place I can use that up. And I can put, in the sulfur, I can put a 3 over here, because this is the only place I can use it up. And I have it to start with, so I've got to use it up. And those are the only 2 ways I can use it up. So I threw a 2 and a 3 over there. Kind of took you to the next level, right? Before we would do the 2, figure it all out. Now let's do the 3, do it all out. And now we said, you know what? Might as well do them both, because those are the only places we can use them. But because we did 2 products, we changed the coefficient on 2 products, we're going to recount the counts on all the products. So nitrogen, let's go from left to right. We have 3 sets of 1, or excuse me, 3 sets of 2, right? Yep, 3 sets of 2 for 6. 3 sets of this molecule. Each molecule has this polyatomic ion. Each polyatomic ion has 2, so 3 sets of 2 is 6. Hydrogen, it only appears in the ammonium. Each polyatomic ion has 4. There's 2 polyatomic ions, which is 8, and there are 3 molecules, which is 24. Chlorine, it only appears in the aluminum chlorate. There are 3 polyatomic ions. Each one has 1, so there are 3 times 2 is 6. Oxygen appears in both molecules, and that gives us 30. I have 3 per poly. 3 polys is 9, and 2 sets of 9 is 18, plus each sulfate has 4. There's 1 sulfate per molecule, and there's 3 molecules, which is 12. So 18 and 12 is 30. Aluminum, it's just in the first molecule, 2 of them, 1 per molecule. Sulfur, the last one, 1 per molecule, 3 molecules is 3. So now I'm balanced with respect to aluminum and sulfur, the 2 I adjusted last time. I'm unbalanced with respect to everything else. Okay. Now, oxygen appears in more than 1 molecule, so I'm going to choose to not deal with oxygen right now. And the magic is, it'll probably take care of itself if I don't worry about it. And if I have to worry about it, I probably have an elemental form somewhere that I can adjust. But for right now, since I would have to decide, if I start to attack oxygen, I would have to figure out which of these I'm going to increase in by how much, and just arbitrarily make it up on my own. So let me deal with something else that's not arbitrary, something that I actually, from the formula, figure out I have to do. But look at, I was told that I used up 6 nitrogens, but I only have 1, so I need to have 6. And how am I going to do that? If I put a 6 in here, I have 6 nitrogens to use up. Oh, but look at hydrogens. I say I have 4, but I used up 24. I need 6 times as much, which, hey, this is the only place it comes in. You know what? I bet you if I clean up my nitrogen and hydrogen need, my oxygen need will take care of itself. So I throw a 6 coefficient up here and recount all the reactants. Nitrogen, 6 sets of 1, which is 6. Hydrogen, 6 sets at 4, which is 24. Chlorine, 6 sets at 1, which is 6. Oxygen, 6 sets at 3, which is 18, plus 3 sets of 4, which is 12, which gives me 30. Aluminum, I didn't change that, it's still 2. Sulfur, I didn't change that, it's still 3. Now it's a balanced reaction equation. And a couple of you, what problem was this? Do you remember? This is number 6. So in at least one case, you wrote down 6, period, NH4ClO3, plus, okay, I counted the 6, which was your number place, as part of your answer. I gave it to you, okay? Now, you can argue I should have or shouldn't have, but I'm thinking to myself, you wrote down 6, okay, what's this? Let me balance it, let me write it up. But first thing 6, oh, I already wrote 6, okay, see, I gave you the benefit of the doubt. I might second guess myself later, but for now, I gave you the benefit of the doubt. So, any questions on number 6? Okay. Let me back this up just a minute. Number 7 says, in an automobile, nitrogen from the air reacts with oxygen in the engine to make nitrogen monoxide. Write the balanced chemical equation for the reaction. Okay. It says nitrogen reacts with oxygen to create nitrogen monoxide. So we've had 3 things going on here: nitrogen, oxygen, nitrogen monoxide. Now, if I said carbon dioxide, what would you give me as the formula? Carbon dioxide. Okay, it's a covalent molecule, so it uses CO2. If I said carbon monoxide, you would reply with CO. If I say nitrogen monoxide, you give me NO, right? Now, it says that nitrogen and oxygen react. When they react, what is their form going to be? Their elemental form, which is a homonuclear diatomic, which means you might write down initially N plus O reacts to produce NO. But we don't have elemental N and elemental O available to us. It goes to its homonuclear diatomic form, which means we're looking at N2 plus O2 react to produce NO. Okay? N plus O doesn't happen. N2 plus O2 produces NO, but this isn't balanced, is it? Because you can see right here that if I look at this, I've got nitrogen and oxygen, and I've got 2 and 2 over on this side, 2 and 2. And on the product side, I have 1 and 1. So, obviously the hardest part of this problem is not to balance it once you have the right reaction equation. The hardest part of this problem is get the right reaction equation. That nitrogen and oxygen react to produce nitrogen monoxide. Now I know I've got 2 reactants. I haven't used up all my reactants, so to use them up, I need to add a 2 coefficient in front of the product, and then I get 2 and 2. Now it's balanced. That was the whole number 7 right there. But it hinged on your ability to know that nitrogen and oxygen react, that they have to be in their homonuclear diatomic form to produce nitrogen monoxide, and you had to correctly write nitrogen monoxide. So this problem here was mostly from several modules ago. And just this last portion here of 2211, let me add a 2 coefficient to the nitrogen monoxide. There we go, we're done. All right. Shall we get started with 8? Let me say that in a more, shall we get started with 8? I have a speech impediment sometimes when I'm rushing. Man, it's all over the place. So, number 8, we'll start it at least. Liquid heptene. Can react with gaseous hydrogen right? To make liquid heptane. So, write the balanced chemical equation for the reaction. It's lame. Try to go small, it turns into an O. Here we go. Let's make it bigger. Carbon, hydrogen. Any more? Nope. All right. To count on the left. What is it? And 12. Count on the right for, these are the reactants. And the products, count on the right is and. Okay. I have no place where I have remaining reactant. I've got one place where I have insufficient reactant, right? I've got more product. So I need to come up with 4 more hydrogens. What am I going to do? Yeah.
You're going to put a 2 in front of the H2.
No, I'm not. Ma'am? You put a 3. Because if I put a 2 up there, I'm only adding 1. Remember, a 1 is implied. There's already a 1 there. I need to increase it by 2. 1 plus 2 is 3. If I just stick a 2 up there because I need 2 more, which is the common mistake, okay? If I just stick a 2 up there, I've only added 2. Because 2 is only 1 more than 1. But to get 4 more from the molecule, I need 2 more molecules. So I need to take the 1 plus 2 is 3. So if this becomes a 3, like that, now the only thing I've changed is hydrogen, and I get 10 plus 6, which is 16.